Hello, everyone. Thank you for joining us for the 3D displacement and strain measurements with high-speed camera webinar. We have two great presenters today, Tim Schmidt, Vice President of Trilion Quality Systems, and Shane Kersey, Applications Engineering Manager at Photron. Both are experienced and respected in their respective field. So sit back and enjoy. We will have time for Q&A near the end of the webinar, and our speakers will stay a little after the webinar to continue answering questions. Any questions that may come up during the webinar, please go ahead and type them in the Q&A section. All right, we're ready to start if you are.
All right, thanks, Ben. This is Tim Schmidt, and what we're going to be describing to you today is ways to extract quantitative data from high-speed video. And typically we'll do that using a pair of cameras like you see at the top center image, looking at a surface that's been prepared one way or another. And then we get out lots of interesting data. The bottom example is the mode shape of a vibrating panel. We're going to look at hovering helicopter rotor blade vibrations. We're going to look at ballistic impacts, bomb blast effect testing, a lot of things like that in the next hour. So thanks for joining us. Today is a National Day of Mourning, and Shane and I both felt it wouldn't be right to just talk shop without taking one moment to acknowledge a man who spent many decades trying to serve the country as best he could. I also would like to point out much thanks to Sully, the service dog. This is really quite a remarkable picture here. So what we're going to go through in the next hour is a few background words about Trilion, GOM, and Photron. Who are we? What do we do? What is point tracking videogrammetry? And what is digital image correlation? These are the two primary measurement techniques that we do with the high-speed cameras. I'm going to show a few examples of quantitative measurements at low rate and high rate. Shane will give a lot of background on the different cameras within the Photron product family and how we take advantage of those features to make measurements, and lots of examples. That's the main thing we want to show you, kind of stimulate your imagination on what kind of measurements you can make, displacements and strains with the high-speed cameras. And then what's new and what's next, and any questions that you have, we'll be glad to try to answer. So Trilion is the exclusive distributor for a larger German company called GOM. We've been doing this since about 2001. We've got over 600 systems delivered and closely supported. We do a lot of application development, figure out how to make new measurements for the first time. And high speed is actually a great example of that. We started doing it about 3 or 4 years before it was being done by GOM in Germany. And we do lots of services as well, both at low rate and a high rate. So in fact, we own a fleet of 10 Photron cameras ourselves that we use for demos, services, and rental of high-speed measuring systems. So we've been growing rapidly. We moved into new headquarters about a year ago. This is most of our team. We're going to have to take a new picture in January, so Ben will be included. Right now he's working invisibly behind the scenes, but thanks, Ben, for organizing this today. As I said, GOM is a much larger company in Germany. They've got about 500 employees. They've been around since 1990, 50 programmers. So the software is the real differentiating factor in making these kinds of measurements. They've got about 60 distributors worldwide, of which Trilion is the largest for deformation and strain measurements, and worldwide about 14,000 systems delivered. They also are an OEM integrator and reseller of the Photron cameras worldwide. So overall, basically, we use a lot of Photron cameras to do high-speed measurements. GOM has a wider range of metrology products. We're going to focus today on what we call Aramis, which does the displacement and strain measurements. And it's, again, used worldwide in pretty much every industry. How do we basically make measurements? Again, it's a stereo pair of cameras with an angle between them. They are co-aligned to be looking at a certain measuring volume, as we call it. That measuring volume might be 10 millimeters wide, it might be 100 meters wide. It's whatever is needed for the application. But basically, if we've got markers on a test object within that volume, we can get out the 3D coordinates, the shape, the displacements, and the strains. So a typical setup, therefore, you're going to see lots of setup photos in this presentation. Typically, you're going to be seeing a pair of Photron cameras of one model or another like this, arranged in a stereo pair, looking at a test object that has some kind of preparation on the surface, and we'll talk about those details next. So in this video, we're adding highly quantitative deformation data to the prosthetic as a person is running. We've simply put a number of discrete point markers on there. There's actually a lot going on here if you think about it, because we've removed the rigid body motion. It's as if that prosthesis was being held stationary, and we're presenting only the deformations of it. This is one of the basic features of the measurements that we make. We can quantify rigid body, but we can then also remove it and show only the deformations. The key to photogrammetry, or measuring with cameras, is that we're working with sub-pixel accuracy. Our dot markers are typically 10 or 15 pixels diameter. We're finding the centers of them with 1/100th of a pixel accuracy. So lots of measurements can be made just with a relatively small number of these point markers. This is a baby wind turbine. This is an 18-meter one. We do the same on 100-meter ones, and we've targeted the blades and the tower. It's a lot of work with a traditional instrument just to measure the bending of that tower. You see those large steel towers. Those are to hold the other end of a draw wire, and so those towers have to be stronger than the wind turbine itself, so you would hope to get accurate data just bending at one point in one direction. We've got ground-based cameras, and we can measure all of the displacements in all three directions and all of the vibrations of the blades as well. We can get a lot of data just from having a couple of marker points. Here I've shot a titanium wedge out of a gas gun, and there's just a few point markers on it. But what we're able to do in the software is simply make a best fit plane in every image and then do angle analysis. So very shortly after the test, we're getting a chart of roll, pitch, and yaw angles and rates, as well as velocities and accelerations. So a lot of people call this 6-off, 6 degree of freedom analysis. Many times we'll do this instead. We've spray painted a random dot pattern onto a tensile test specimen. And so now we're getting strain at thousands of points. So we're seeing all of the local strains and the necking effects. So these are the two basic types of measurements that we can make. Basically, we're spray painting on 5,000 3D displacement gauges and strain rosettes. The way that works is actually quite similar to the point tracking. We're defining pattern matching boxes, 15 or 20 pixels square, and we're tracking the centers of those the same way that we would track the centers of individual dot targets. But what DIC actually does is quite remarkable behind the scenes. This is all happening completely automatically in the software. I've drawn a couple of the pattern matching boxes. This is a pattern runner's foot, obviously, and the pattern matcher stays locked on to those random dots and reports the center out despite all the rigid body, despite the deformation. Here you're seeing a lot of rotation. Doesn't matter, we're staying locked on. So that's basically what digital image correlation does. If we compare that to traditional measuring devices like you would use on your MTS load frame, typically we're getting out one data point. We're either tracking just the crosshead travel itself and reporting that as the average strain. We may be attaching a clip gauge, a mechanical extensometer, and getting the average data between 2 points that way. More recently, there is a trend to doing video extensometers, but typically you're just getting data from a pair of points. Compare that to the DIC, we've got 5,000 virtual strain rosettes, so you're seeing that very local behavior. You're getting a lot more insight into things like material behavior. You're seeing Luder's bands, shear bands, even much more than necking that I showed before. So that's why we do these optical measurements. We get a lot more data, and it's pretty easy and quick to get this data. How accurate are we? It does depend on the resolution of the cameras. This chart is for 4 to 6 megapixel cameras, which some of the high-speed cameras are. Our displacement accuracy scales with the field of view. Strain sensitivity is constant. It's 25 to 50 microstrain for 4 megapixel cameras. For 1 megapixel high-speed cameras, it's still below 100 microstrain. Not as accurate as strain gauges, but I've got 5,000 of them. This is Trilion's own quick overview of the different model cameras that Photron has. They've got a range of mini cameras that we like for a few reasons that we'll show, and then they've got larger, higher performance cameras. But I think it's probably better for Shane to take over and talk you through the fundamentals of high-speed cameras and what kinds Photron has and what they do.
Okay, thank you, Tim, and thank you, Ben. As always, it's good to be here with you. So yeah, this is a really good slide because it shows you some of our most popular cameras. So we've got the Mini family, which has a very small footprint relative to other high-speed cameras. And we have different capabilities. So there on the left, we have the 4 megapixel. We have a couple of 1.3 and 1 megapixel cameras. Different specifications, we'll get into the details of those later. But very nice, small, lightweight cameras that are very powerful. And then we have the SA, which stands for standalone cameras. So used to, we would have you would have to have a PCI-based camera or something like that. So the SAX2 and the SAZ have higher specs. And as you can see, they probably look a little bit bigger because they are a little bit bigger, but you're getting up into the 12,000 frames per second at full resolution, 20,000 frames per second at full resolution. And these cameras will go up into the millions of frames per second at smaller resolutions as well. But before we get into all the details of the cameras, let me tell you just a little bit about Photron. So today, kind of interspersed during the presentation, we'll talk about the software, which is PFV, which stands for the Photron FASTCAM Viewer, and we'll talk about some cameras as well. So Photron has over 40 years of experience in the high-speed industry. We've been doing this for quite a long time. We are a worldwide leader. Everyone knows that knows high-speed camera, knows Photron. They also know the 2 or 3 other companies that we compete against. And what I always like to say is everybody makes good cameras for certain applications, but Photron, we believe in having really good quality, good sensitivity, and those are some of the things that you'll see come out that I believe put us of about that later. 1991, the Model 4540 was launched. At the time, it was the world's fastest commercial high-speed camera, and it would do full frame up to 4,500 frames per second, which at the time was amazing, but now it's kind of average. And then years later, we were the first company to have a megapixel resolution over 20,000 frames per second with our SAZ. And for those of you that have been in the industry for quite a while, you might go back to the Kodak days. And this is a picture of the Kodak camera. But what a lot of people don't know is that Photron actually made that camera and Kodak just slapped their label on it. Well, through different circumstances, Kodak got out of the high-speed digital camera world. So Photron just began to brand that camera with our own label, and that was kind of the impetus for Photron starting to brand our own cameras. Now, Photron today has a very wide range of cameras, and we're known for our reliability, among other things. We do have a 2-year warranty, which I believe we were the first company, the high-speed company, to have that. And as most of you probably know, that any military range, national lab, or university you go to, you'll see a Photron camera there, for almost certainly. Now, the North American support is all done from here in San Diego, California. And here from San Diego, we support North, Central, South America, Australia, New Zealand, and Israel. And as you can imagine, across that territory, we have every imaginable application. Now, what's unique about the Photron cameras, or specifically we're talking about the FASTCAM family of cameras? All of our sensors are unique sensors designed by Photron, which is the case for most high-speed companies, but there are some out there that do use off-the-shelf sensors. The sensors are all 12-bit sensors. Some of our sensors you can run in an 8-bit mode that would give you a longer record time. We have what we call dual slope shutter. Some applications you're going to get bright flashes, and you're going to have self-illuminated events. We'll talk about how we can use this dual slope shutter to overcome that. It's a very interesting feature. Fast gigabit offloads. Usually the high-speed camera guys are what hold up the test, so getting that data off as fast as possible is always important. And some of our cameras do have what we call dual gigabit offload, so you have two ports where you can offload data twice as fast. Again, the Mini family, we have the 1.3 megapixel, what we call kind of the entry-level Mini is the Mini UX. We have the 4 megapixel, the WX, and the 1 megapixel Mini AX. Some of the features of the Mini cameras, again, the unique sensors, only 3.3 pounds for a very powerful camera. These cameras are rated up to 100 Gs. We have customers that will mount them inside vehicles doing rollover tests, and so they withstand that kind of abuse very well. And some of the university professors like it because they feel that if their students drop the camera, maybe they won't have to buy a new one. Again, we do have 12-bit sensors and bit shift, which is very interesting. We'll look at some of the benefits of that, but again, these are 12-bit sensors. Your computer screen can only show you 8 bits at a time. So there's always more data, and that's what we're very interested in, is getting more usable data out of the image. And we can do that with some of the nice features with our software and our cameras. These mini cameras, the Mini AX specifically, does go down to a 260 nanosecond exposure time. So if you need to stop that fast-moving event, you're going to need a short exposure time or a laser pulse, depending on what your application is. These cameras do go up to 32 gigs of internal memory, and you can segment that memory up to 64 segments. So if you have a repetitive test where you only need a few frames per test, you can just partition that memory, and then that way you can trigger into different partitions, and it makes it very easy to segregate that data. So you're not spending hours and hours at the end of the day trying to segment that up into per test. And these cameras do have a very good light sensitivity, 40,000 mono and 16,000 color. The 4 megapixel and which is the WX and the UX, are not as sensitive, but the AX is a very, very sensitive camera. And I'll turn it back over to Tim.
Right, thanks, Shane. I want to show some examples of why we like to use the mini cameras. We use them whenever we can because of primarily because of their lightweight. It makes it very easy to get them into a little bit more difficult setups. So this is a shock table test. The unit under test is not a bowling ball. It was confidential, so I've blacked it out. But it was a electronics unit that had a joint in it, and we were studying motion at that joint. So playing back shocks from certain real-world events. But you can see with the mini cams, I'm able to get in there and just work off a tripod and have the cameras looking down. Very convenient to use. This is the complete shock event. So with rigid body, we're basically quantifying the shock, checking that the shock is behaving as expected. Then we can wipe away the shock and be left with just the relative motion at much lower amplitude. So we were picking out 18 to 20 micron differential motions during that shock table test using the mini cams. Press deflections is another type of test that we do a lot of, and we take out our fleet of the mini cams. This is another point tracking application. So during press operation, we're looking at how smooth are the motions and what are the deformations and deflections occurring for troubleshooting the end result in the stampings. Our German partner made a little fun demo with the mini cams. I just got the details of this yesterday. So they took a balloon from one of their weddings recently, and I'm calling this the how to break a heart test. Punctured the balloon with a dart. I don't know if this bodes well for the marriage or not, but pulling out lots of quantitative data. I'm not going to show the movie, but lots of things of interest here. We're tracking the motion of the dart with points on it. We're measuring strains, velocities, and accelerations on the balloon during the bursting. So you see we're reading out here the velocity of the dart. We're reading out the G level, and surprisingly very high, 5,000 plus Gs in the response of the balloon to being bursted by that dart. And again, quick, easy setup using the Photron mini cams. When we needed higher performance in the past, we would use larger cameras. I made a whole presentation called How Do We Try to Abuse Photron Cameras. We've not ever really been able to break one or stop it from working, but we do put them in some pretty crazy test situations sometimes. So here, we've got that pair of Photrons, as usual, on a longer camera bar, looking at a larger field of view. The measurement was rocket-assisted takeoff of a target drone, and measuring the shifting of the Rado bottle during the launch. So this is the early stage of flight. I'm not able to show results, but I just want to give you a feel for the kinds of applications that we do. The cool thing is that now the mini cams have the same performance as a number of the older model Photron cameras, which in fact have been discontinued because you get the performance now from smaller, lighter cameras that are easier to manage. This was actually the very first high-speed test that I ever did back in 2003. This was done with different cameras, but the defects here are not due to the cameras. They're due to my inexperience and just what happens in this kind of test. And so you're seeing this flash that occurred and momentarily whites out one or two frames of data. Whenever I talk about high speed, I have to acknowledge Dr. Chris Conley from West Point, because he got myself and Trilion started back in 2003 with high speed, and it's been really a nice adventure ever since then. He's about to retire, but I'm always grateful that he came up to me and asked, could we make measurements with high-speed cameras? And I said, I don't know, but I'll find out. And we've been making measurements ever since. So, but that momentary flash, was a problem. And luckily, there is a solution that Shane can describe to you.
Right. Thanks, Tim. So, yeah, this can be a problem not just for events like we just saw, which are what we call self-illuminated events, right? But it can also be a problem for something simple that you're just looking at a very reflective object, especially if it's a cylindrical object. You're almost always going to have some glare. So we have what we call dual slope shutter. And what dual slope shutter allows you to do is actually during the recording, it allows you to reset each pixel's exposure. But the key is to this is that it does it at the pixel level. So imagine if you're looking at the image that we just saw, there were some pixels that were not overexposed. They were fine. And so the dual slope shutter during that recording, it would not have reset those pixels. But any of those pixels that did get overexposed while the recording's taking place, every single frame, and you can do this at hundreds of thousands of frames per second, but every single frame is going to look at those pixels, and if those pixels get ready to saturate, it's actually going to reset those pixel values so that you can have a very bright event. You're looking into a fireball, but the key is you do have to set this prior to recording. Once a pixel is saturated, there's really nothing you can do to try and retrieve that data. And you know, with really bright events, you're always going to have some saturation. There's really nothing you can do about that. But the key is to get as much usable data out of the image as possible. And now this is a good example. So these are 4 individual images. The backlight of these images is all exactly the same. And if you look at this, so we're just at 6,400 frames per second with a 100 microsecond exposure. And here the dual slope shutter is off. So you have a very saturated image, pretty much an unusable image. And here we've set the dual slope shutter. So basically it's at 50 microseconds through the exposure. It's looking at every pixel, and any pixel that is going to be saturated, it's going to reset that. But even with 50 microseconds, you still get a lot of saturation. So on this image, we see here that we've adjusted the dual slope shutter to 80%, which means that any of those pixels that we're not going to saturate, it leaves those alone. But any of those pixels that were going to saturate, now it's reset those so that they have a 20 microsecond exposure. So just with setting our dual slope shutter to 80%, we've gone from a almost unusable image to a very usable image with lots of data. This first image here on the left is dual slope shutter set at 90%, and that's actually a little bit dark. So probably the 80% in this example would be good. But just with this feature, you're able to go from an unusable image to a very usable image. And we have a real world example here. So this is actually looking at the main gun of an Abrams tank. And the center image has dual slope shutter set at 0. So it's turned off. And then the top has the dual slope shutter set at 99% and the bottom at 95%. And you'll see that you're still going to get some saturation. But now compare the top and the bottom images to the center image. If you're looking at the profile or the propagation of this flame, well, then maybe some of the saturation doesn't matter. But if you're trying to look inside this ball of fire and see some of the texture and some of the properties of this flame, well, then setting the dual slope shutter really gives you a lot more usable data. And we'll let it play one more time because there's another thing you can gain from this. With the dual slope shutter, you actually see the projectile exit the fireball sooner. And then we're also going to see the sabot separate from the projectile, the penetrator, earlier when the dual slope shutter is on or off. So again, we're taking the same test and we're getting more data out of it. Because it's not always about pretty pictures. Everybody wants pretty pictures. It's about usable data.
Right, so we did get usable data from this air blast test. But we would have gotten more using the dual slope shutter. I want to highlight now the difficulties again and limitations of traditional measurements. They had put 3 rod devices to try to get single point displacements, and they basically turned to spaghetti and or blew out of the panel during the test. It's really difficult to instrument explosive events. We got the complete data. This is the initial flatness of the panel, which is a bonus kind of measurement that we get. This was my main result, this triple lobed displacement effect from the pressure wave impacting the panel. This was 2 pounds of pentolite 2 feet away from the panel. So we do a lot of explosive effects testing. Here you're seeing the Photron cameras, stereo pair behind a protective wall, just out literally in a farm field down outside Nessa Marshall, running off a generator. These are typical field conditions. The test object is here. If you look carefully, yes, it is bolted to a fallen tree. And yes, this is a real NASA test facility. That's the fun of the job, is to go out and see these real world high-end, this literally is a high-end test setup. But just for fun, it is bolted to a fallen tree. It's explosive effect testing. This was done by Bangham Engineering. I think they're acknowledged on the next slide. So gunpowder loading and looking at the deformation of different sheet metal alloys. On these outdoor kinds of tests, you get into issues with sun shadow and just widely varying and sometimes hard to control illumination levels. And again, there's a feature in the Photron cameras that helps with that kind of negative influence during outdoor testing.
Right, and this is where we get into having 12 bits of image data, but only being able to see 8 bits on your computer screen. Just remember that there's always more data in your image than you're seeing on your screen. And one of the ways that we address that is with what we call high dynamic range, or HDR. So HDR is an algorithm that allows you to display as much usable data in a single image. Now, you're probably familiar with HDR on your iPhone or maybe your DSLR, which takes different images, maybe an underexposed image, a properly exposed image, and an overexposed image, and actually combines those images together to give you beautiful sunsets and portraits and all those type things. So HDR with Photron, because we're recording at high speeds, you can't do that. You can't take multiple images at different exposures. So what we actually do is we utilize those bits that normally are not seen to pull up that usable data out of the dark areas. So you do this in the live image. You can basically, if you turn on HDR with your live image, it appears as if you're bumping the gamma or adding gain, but you're not. You're just seeing data that's already there. Or you can do this as a post-processing tool as well. So for any of you folks that have 12-bit data that you recorded years ago, you can always pull that back into the Photron software, run this HDR, and actually get more data out of that image possibly. And so here's just a very simple example, all right? So we have a speckle pattern here with just a fluctuating backlight, all right? So I'm sure Tim looks at this speckle pattern and is disgusted because it's just something that we're playing around with. But don't worry necessarily.
Shane, that's the sound. That would work.
So we got this area on the outside of our rubber material with the pattern on it. We're not really concerned about the saturation there. We could have used dual slope shutter to get rid of that. What we're focused on is this speckle pattern in the center, and what we see is that obviously our grayscale is fluctuating. We're getting brighter and darker. So the GOM software Aramis could probably run, and really do okay with this. But visually, we're seeing this, and it's not very intuitive what's going on as if we were actually had a real world event. So what I've got next. All right, so now this is the exact same video that we've just turned on the HDR. So now we can see the exact same video. You're still going to see the saturation on the outside of the image. Again, we don't care about that. But actually the area of interest now, we have very little fluctuation in the grayscale. So the image now, when it was darker, we're just pulling up some data out of those lower bits that you weren't seeing before. And when the backlight brightens up, we're just using those upper bits that you were seeing before. So now we've got a very stable area of interest. And just a quick side by side here, just to see the difference. And so you can imagine, excuse me, in a real world event, say for instance, you're looking at something, the cloud passes over it, it gets dark. You can pull up data out of that dark image, or say perhaps you're looking at something that's you have some shadows, or you're trying to look into a room that you're doing tests in, and the outside of the room or the wall that's being tested is perfectly illuminated, but inside that window or inside that doorway you have a dark area. Well, this HDR can pull up the data out of those dark areas without saturating or without blowing out the areas that were properly illuminated. So it's a very nice feature that we have both in PFV3, our older software, as well as a better algorithm now in the PFV4.
Right. In the past, I would do pre-processing of high-speed camera images. I would do histogram equalization in third-party software to try to get rid of some of those effects. So it's really nice to see that that's kind of built into the Photron software now. We did get nice explosive response data on a lot of panels down there. I kind of like this one. If you look at, this was a non-brittle response, a ductile response, but it always looks like something from a sci-fi movie. There's kind of an alien ship opening up and about to eat the Earth or something. But again, explosive effect testing done outdoors with Photron cameras through protective windows, the kind of tests we do a lot. We're going to have to speed up a little bit to leave time for questions. So I'm going to whip through different application examples now. A little bit larger bomb blast effect testing. This was a truck bomb equivalent. So we're talking a couple of 100 pounds of C4 where we might be putting the cameras behind bomb proofs like you see here. We might be putting them inside a target building. So you're seeing there the pair of cameras staked down through the floor to the ground. We're doing our typical DIC preparation on the right, the patterning and calibration of the cameras. This is 4 images from the video showing initial response. Just the bottom left is responding. Then the individual wall boards between the beams are individually moving. They start to link up, and then later the whole side of the building will buckle. This is a magnified view of the 3D displacement. So it's a nice visualization tool just to give a feel for what happened in that test. This was an untreated building compared to a treated building. And of course, we had the Photrons in the good building. We want to take care of the cameras. Yeah, lots of ballistic impact testing. This is the old days of ballistics testing. This kind of go, no-go testing is kind of frowned upon these days. So it's good that we're able to do DIC and pull out quantitative data on test objects. I'm not going to play this video to save time, but we've got a couple of Photron cameras in a safe room looking at the response of a suppressor on a 50 cal automatic weapon. Whoops. Had a little event here. One of the shell casings, this really happened. One of the shell casings got embedded in our camera bar, luckily not in the Photron camera. Shane does have stories to tell about unfortunate events with Photron cameras. This is a 50 cal rifle on a range mount up at West Point. So you really gain an appreciation. I always say when I go up there, it's really an honor and a privilege to be able to try to make even a small contribution to warfighter safety. When you're needing to wear a helmet and a vest, and when the colonel and cadets are leaving the building for safety and you're left alone with the gunner, it makes you really 1% maybe appreciate what the warfighter is really going through on a daily basis. What we did for the cameras here is make a custom enclosure. So we've got the Photrons in an armored enclosure with Lexan windows with some adjustability. So we at Trilion make this kind of custom supports and enclosures for Photron stereo pairs. The gunner's job was to make sure my head was below the armor panel before he fired the gun. So interesting day of ballistic testing. This is from a different test, just to show typical ballistic impact response. This is small arms fire on a helmet. And the helmet, of course, is just loosely mounted to a head and shoulders torso. So there is a lot of rigid body. The picture becomes clearer just looking at the time history of those points. The raw data is dominated by rigid body. That whole helmet is being pushed away from the cameras, and the magnitude of that is obscuring the vibrations that we really want to see. Now, this might be useful. We can see by coincidence it moved 14 millimeters in 14 milliseconds, so we know the velocity. We get some momentum transfer data. This is what we really want, and the DIC software does this correction with the click of a mouse. We remove the rigid body. This is the corrected data showing the vibrations about 0. So that's an important and powerful feature of DIC. There's lots of post-processing that can be done. ARL SLAD, Dixie Hisley, and James Gerganis and Joe Lee have been doing a lot of work. This is also showing our ability to measure not just displacement and strain, but also velocity and acceleration. And if you look at the G levels, we're talking quite a high G level. That's not so easy to measure with accelerometers, and so it's easy to do optically, actually. Another just general example, Photron cameras in interesting places. There's a pair of Photron cameras on a large custom camera beam, and we're looking down, as you can see, on a hovering helicopter, and we're actually measuring the vibrations of the rotor blades. So we have ways to calibrate large fields of view pretty quickly and easily, and that's what they're doing there. And then just a very quick look at the results. This is where we're holding that rotor blade stationary and looking at the operating deflection shape. So that's our raw data, is the operating deflection shape. In the world of vibrations, it's of great interest to then be able to extract mode shapes. UMass Lowell has been doing work on that for many years. We're going to talk soon about tools that we've developed and integrated into the Aramis software to do vibration analysis. I'm just whipping through some very quick examples here. My colleague DJ does a lot of work on pumps and pipes as one example, and just operating machinery of all different types. So we've added in, we call it our FAST module. We've added in the ability to pull out single point FFTs like we're showing here. We've also developed the ability to extract the mode shapes from the operating deflection shapes. And again, there's a lot to talk about there, so we'll do that some other day. These are Hopkinson bars that Trilion actually manufactured and delivered to Howard University. So when your high-rate MTS machine is not high-rate enough, the Hoppy bar is a very high-rate loading apparatus. We're doing 1,000 strain per second typically. So that's what Hoppy bars do. And you're seeing a custom camera mount here holding the pair of Photron cameras vertically to look at a 0.1 inch long compression specimen. Micro positioning of the cameras to get these very small fields of view co-aligned very, very easily. So it's the similar problem or limit with traditional instrumentation. They're getting a single point of data, and they're not even directly getting it. They're inferring it indirectly from strain gauges. We're able to directly measure strains on the specimen. This was our validation. We're able to measure in the necking, which cannot be done at all otherwise on this kind of Hopkinson bar test, but we've introduced the ability to do direct strain measurements and measure necking optically. I'm going to whip through this, Shane, because we
go ahead.
Finish in about 10 minutes. That's a kind of application that requires higher performance than the mini cameras can do. So Photron has this line of higher performance cameras, the SAZ being the top of the line. And so we do use and sell a lot of these top performance cameras. They're doing 21,000 frames a second at the full 1 megapixel. And as we showed before, you can reduce the resolution and go up over 1 million. We're typically using them up to 200, 300,000 frames per second, or we're getting more resolution at the lower frame rates. That's the general benefit of these cameras. I'll skip through this stuff. The fast drive option is something I do want to talk about, and I'm going to show an application next. Shane mentioned the desire to get the pictures off the cameras very quickly, and this is even faster than getting it off the camera to a laptop. It's the integrated fast drive that lets us directly dump the camera RAM onto this drive and be ready to run another test very, very quickly. That was a critical feature of these cameras for some tests that we did. So statically, we do micro motion analysis where we're looking at small shifts between orthopedic implants and the bone. So this is an example where optically, even though this knee simulator was rotating back and forth, we're staying locked onto it, de-rotating it effectively and putting gauges and showing the motion not just in line, but also out of plane and in the shearing direction. There's also a desire to do that at high rate. So this was a drop test. Again, I'll skip the video. at about 12,500 frames a second, we were looking at the hammering down of the head onto the stem of an implant. You won't actually see very much in this video. You'll see a little bit of shifting in the vertical direction as we're using a drop tower to simulate installing the head onto the stem. Complicated 3D geometry, but the DIC can lock onto that. What we were seeing was these non-linearities in the insertion process. We sped up the cameras just by reducing the resolution. Nothing else needed to be changed in that setup. We cropped the field of view, went faster, and saw that these discontinuities were really, really occurring. We're also doing real hammer hits onto the implants. Here we're using an interesting feature. We have a laser trigger where basically this application demanded all the best features of the Photron cameras. So we're using a laser trigger. You're seeing that here. As the hammer passes the laser, it triggers one partition in the Photron cameras. And less than a second later, when the next hit is made, we trigger the next partition, and we're also recording the analog data from the accelerometer on the hammer. So there's really a lot going on in this test. And this was really critical for the customer because much like a car repair, it's the labor, it's the surgeon, not the parts cost that's really high. They were paying the surgeon the going rate to, run these simulations, and they also do cadaver studies. So the ability to trigger one partition at a time and get all the data from a whole bunch of hammer hits, transfer to the fast drive, and just do it again within less than a minute, do a whole nother sequence. That's what was needed, and that's what we got using the SAZ cameras with those features. This was Shane's slide. I wanted to talk it through anyway because I can never say enough good things about the support that we get from Shane and Photron. I was sitting in that customer's lab trying this for the first time and realized I wasn't sure. One thing, was it going to work at all? Are we separately keeping the analog data in each partition? I never thought about it, never tried it before. I called Shane, and he's like, I think you're the first person to ask that question. No one ever needed to do that before. I'll make a setup in my lab, and I'll call you back in half an hour. And I mean, he did. He just made a setup, found that it worked, and called back and told us how to do it right on the spot. So we're blown away by the support that we get from Shane and Photron. So this is just a quick example of differential motion between the head and the stem during a hammering test. We did make a custom stand to hold the Photron cameras low to the floor for that drop tower test. I'm just looking at the time. So the disadvantage of the SAZ camera was that it's a little bit big and heavy. We can make it work, but it is a little bit big and heavy. But again, Photron has a solution to that problem as well, and I'll give it to Shane to describe this.
Thanks, Tim. So, yeah, this is the newest Photron camera, the FASTCAM Nova, and we're really excited about this because it's got 12,800 frames per second at a megapixel, which is not quite as high spec as the SAZ, but just a step below that. And we can go up to 1 million frames per second, 200 nanosecond exposures, which, for 99% of applications is more than enough. But then we've got this ISO 64000. So this is going to be, or it is, the most light sensitive high-speed camera on the market. And so you're going to be able to really get more usable data out of the image with this camera. And I could talk about it for a long time, but we want to speed through this. All of these come by default as sealed range version cameras, so that all the electronics are sealed from dust and debris. We do have dual power inputs. If you wanted a battery backup, you can plug that in. And then, as Tim said, it is fast drive compatible, so we can plug in the fast drive and get that data off very quickly. And for those folks that want to use a Canon EF lens, you can use that and control a Canon lens directly through the Photron software.
Yeah, so we're really excited because that Nova camera is kind of the best of both worlds for a lot of the tests that we run. We're getting the higher performance and the fast drive functionality in a much lighter, smaller camera. So we're really looking forward to using those. Next time we're going to talk about things like automotive testing and you know, comparing the old ways and the new ways there. I found this picture, and it was funny the first time I ever picked up an automotive crash dummy. I never thought about the fact that they have to weigh as much as a person. So that's a 175-pound dummy that my colleague Yanni was just kind of carrying around. The reason I wanted to show it, though, is not that. It's this. It's a pop-up from our neighbor Photron at the Auto Test Expo many years ago. We're dating ourselves here because it's the SA1 camera. And this is where it all began. Trilion had serial numbers 0002 and 0003 on the SA1 camera. I think we must be going back to 2005. And I remember learning how to use the Photron software for the first time at the NASA Glenn Ballistics lab, finding that we really liked it. And there we were off and running with the Photrons, and it's been a great many years of working very happily with Photron and with Shane. So I just wanted to kind of end there. Next time we will show lots of interesting car crash stuff and analyzing deformation of bumpers and bringing in CAD to get a really good visual on relative rigid body motion of a bunch of stuff. I think we're going to have to fast forward through this. I'll just mention, Shane, on your behalf, that Photron, as always, has solutions for necessary real-world situations. So they do have a whole other type of camera, these tethered cameras, which are really, really great for onboard and very high G and very compact. And you wouldn't want to blow up an SAZ to get data, but you can blow up a tethered head, and the data actually will be transferred, and the head is gone, but the data is still there. So we're looking forward to using those, and we've done some onboard crash that we'll talk about in the future. But again, as always, Photron has the needed cameras to get a job done, as we're seeing here. I think I'm up to my last slide in a moment. So again, a couple of different models of multi-head cameras with different performances. I'm going to end here with auto crash. My colleagues would confirm that I'm not only the idiot in Idiot Proof, I'm also the dummy in Crash Test Dummy. But nevertheless, I'm going to try to answer with Shane any questions that you might have. We've officially got 5 minutes, but we'll be glad to stay as long as you want to do some Q&A right now.
Thanks, Tim. Thanks, Shane. This is Jonathan, actually, from Trilion. I will be handling the questions. We have quite a bit of questions, so as Tim said, we can stay as long as we can here, no problem.
All right, let me mention one thing, Jonathan, that we forgot to mention. We'll be glad to write up all the questions that you guys have given, type up answers for you, and send it out to everyone. So if you need to leave before your question was answered, we will get you an answer in writing to all of the questions that have been asked today.
Yes, thanks, Tim. And if you have any more questions right now, you can still put them in the Q&A, and we'll try to answer as many as possible. So let's start with this one, which is not really a technical question. Somebody's asking if the slides will be available, and the answer is yes. We'll be sending an email to all the participants with the slides from the presentation, and also a link to the video.
It's not just the slides, but it's also the actual recording of everything we've been saying all day.
That's correct. All right, so more technical questions. The first one, is it possible to use DIC with high-speed cameras on transparent media, especially without patterning?
I think the likely answer there is no. One possibility is it's possible to project dots to measure shape and out of plane displacement only. We have someone doing that to measure thermal warpage of silicon wafers because it's actual manufactured test articles, they don't want any contamination. Usually we do need to be applying a pattern. We definitely need an applied pattern to measure strains because we need points connected to the surface, moving with the surface that the cameras can robustly track. The exception is with projected dots, we can not only get the shape, but we can do some out-of-plane warpage. So that would be my quick answer to that question.
Thanks, Tim. The next question is, how do you paint the speckles on the surface?
Okay, well, so the answer to that question is there's a newer society called IDIX, International Digital Image Correlation Society. They asked me to prepare a course on patterning for DIC. I titled it How to Pattern ... Everything. There's 240 slides in that presentation. The short answer is that there's a couple of simple golden rules. We want each dot to be 3 to 5 pixels with about 50% coverage with pretty high contrast. 90 or 95% of patterning is done with normal spray paint. There's some simple techniques that we teach on how to control the dot size from certain cans of spray paint. There's alternatives of rubber stamping. Larger dots are done with templates in different ways. So there is always a pretty quick, easy, repeatable way to do DIC patterning. It is a critical part of the process. And so we do have right now 240 slides, and they've asked me to convert that into a written good practices guide. So I'll be doing that in my free time over the next year or so.
Thanks, Tim. The next question is, are there temperature limits, I assume, for the cameras?
So yes, so the older cameras generally have a 0 to 40 or 45 C limitation. The newer cameras are coming out with a little bit broader temperature range, so usually about -10 to about 40, 45, and I think some of the newer ones are going to be even above that. But Photron is very conservative with our specs, so we do have customers that are using them out in the deserts where we know it gets above 45 C and without any problem.
Yeah, I would add to that, Shane, there is a way to extend the usable temperature range of the cameras. I didn't show this application. We did measurements in the McKinley Climatic Lab at -63 degrees C, and we simply had heated enclosures for the camera. So the cameras never knew that they were at -63.8. They thought they were at 20.0 degrees C. You could do the same in the opposite direction with a thermoelectric cooler. So for the cameras, it's possible to make them work without too much added difficulty in virtually any temperature. The same goes for vacuum. You can vent an enclosure out to ambient and work in a vacuum chamber. In case the question was about DIC, I was just doing measurements last week at 1100 to 1300 degrees C. So DIC can be done at elevated temperatures. We can see through radiant glow with filters. There are patterning techniques that survive up to those temperature ranges and higher. Southern Research specializes in re-entry material testing and have developed some ways to do DIC even at those temperatures.
Okay. Another question. How is the performance of these high-speed cameras on shiny surfaces like polished metallic surfaces? Is it needed to spray them?
Right. If it's regarding can we do DIC, yeah, typically we would want to do a flat base coat. Normally we would use flat white spray paint. There are more removable patterns you can use. Developer spray, which is used for crack inspection, is very commonly used as a removable way to put down a base coat that would get rid of the specular reflections. We also use polarizer control in DIC. We polarize both the lights and the lenses. That's a little tougher to do for high speed because it eats a lot of light, and you may or may not have enough light left to polarize illumination at very high frame rates.
Okay. Next question. On what camera models is the dual slope feature available? That person asks if the AX100 or the SA models have this dual slope feature available.
Yes, so all of the SA models have it. The AX100 and 200 have it. Pretty much the only ones that don't have it are the cameras that have a digital sensor, which would be the Mini UX and the Multi. But I think all of the cameras that Trilion has for their demo pool do have the dual slope shutter. And so, yeah.
Okay, another question on the dual slope shutter. What is the maximum frame rate usable when using dual slope shutter?
So essentially, think of it this way. The dual slope shutter is not going to allow you to have an exposure that's less than a microsecond. So that means that once you get up to a frame rate of around 1 million frames per second, the dual slope shutter is really not going to have any effect. So any frame rate slower than 1 million frames per second, you'll get a benefit with using the dual slope shutter.
Okay, I've got a couple questions on calibration. So first question, how is the calibration performed? Do you perform the calibration directly in the PFV4 software, or is it done within the Aramis software?
Right, very good question. The answer now is it could be done either way. Historically, GOM and Trilion, we find the PFV software so nice and easy to use that we didn't feel the need to directly drive the Photron cameras from the Aramis software. In particular, their random one trigger, which we don't see on anybody else's high-speed cameras, makes it really simple to snap and save the calibration images and then import them into the Aramis software. And we can do that with any what we call external camera. Now, having said that, GOM did actually make an integration so that for doing the calibration, it is possible to drive the Photrons from the Aramis software. They've done other integrations. I know it's not directly the question. There's a really cool thing they've done whenever a Photron camera saves images, they're saving basically a log file that has all the camera settings embedded in it in a list. GOM reads that file and automatically reads in the frame rate and sets the elapsed time in the timeline of the Aramis project, which is really pretty slick. So we're very happy with that level of integration of the Photron cameras with the Aramis software.
Okay, another question is about calibration. So what is the method used to calibrate the DIC stereo pair, and how are the errors quantified?
Right. Okay, that's a great question. And again, sorry, in this seminar we skipped over some of the little bit deeper details on how DIC and stereo pairs work. We have calibration objects ranging in size from 10 millimeters up to 2 meters, and that can be used for up to 5 meter field of view. Basically, you take a sequence of pictures with the stereo pair of a known dot pattern at different distances and tilt angles to the cameras. The process is called bundle adjustment, but every dot on the panel is found with that 100th of a pixel accuracy. It's traced back to the left and the right camera. So the primary thing we do in calibrating is we need to figure out where are the two cameras in 3D space for the triangulation. That's what's done with that sequence of pictures. It's a very non-critical sequence of pictures. It takes 5 minutes to do this. We also correct for lens distortions by taking rotated pictures, 4 for the left and 4 for the right cameras. So the perfectly spaced dots appear not to be perfectly spaced, and we can correct for those lens distortions. There's also scale bars certified to 1 micron embedded on all of our calibration objects. And so we're teaching the system absolute distances. Since you probably don't want to know your displacements in pixels, you probably want to know them in microns and millimeters. So I think I answered the full question there.
Right. There was an additional question about
quantifying the accuracy. Right. Sorry.
Right. The systematic versus random error, to be precise. That was
right. So that's a whole major topic within DIC. We call it uncertainty quantification. I've got another course, half-day course, just on all that kind of stuff, where I go through the user variables in DIC. I go through noise, static and dynamic noise, repeatability, and accuracy, and how do we try to address that in every single test that we run. The simplest example, at a minimum, we always do a static pretest. We take a few images of the prepared object, right before testing. That lets us make sure we're getting data everywhere, and it gives us at least the static noise floor of the different quantities of interest, whether it be in-plane, out-of-plane displacements, directional strains. Of course, noise is not the same as repeatability or accuracy. Typically in DIC, the accuracy is pretty similar to the noise. We do try to prove that regularly, right? The only way to prove accuracy is by comparison to a reference standard. We can do that easily for displacements. We can translate a pattern plate with a micrometer stage. For strain, really the best way is direct comparison to strain gauges. And so we do that. We encourage every customer to do that in the training, paint over a strain gauge in the field of view, and we'll do a direct comparison. We've got some publications about that, but that's I think a good short answer to the question. It's a very important topic.
Okay, next questions. There's 4 more so far. So next question, how do you take care of rigid body motions? That person says, I have been using a DIC system which removes some average value of displacement from the whole surface, which is giving me wrong results.
Right. Okay. I mean, again, I'll try to give a short answer. We'll be glad to, converse more by email and exchange more details back and forth. I don't know if I'll have time to scroll all the way back to the helmet test. Yeah, basically, I mean, that's what the algorithm does. The user selects points. It can be all points, or it can be any subset of points. Among the points you pick, we're making a best fit plane separately in each frame of data, and we're doing a 6 degree of freedom mapping back to where it was in the reference stage. So what can go wrong with that? There's an assumption that among the points you pick that there's no deformation. In the training, I have some visuals I go through. If you pick deforming points, then the best fit plane would itself be tilting, and it would be adding nonsense displacements rather than correcting them. Yeah, here we go. So like on this helmet test, I know that if I can see my cursor, this area was having higher deformations. The points I used for the rigid body were up on this non-deforming section. When in doubt, using all points tends to work well. But if we know where there are deformations and we know where there's none or less, we can limit our selection of points. The other thing that's important is to pick points that are separated in 2 directions. So this way and this way. If I only pick a narrow swath of points, I'm not going to be sensitive enough to tilting in this direction. And then the way we can assess it is, was that DC bias removed? Here we see the DC bias. Here we can see I did a good removal because I really am oscillating about 0. If I wasn't oscillating about 0, I could redo the rigid body correction, selecting different points. We've got more fancy tools in the Aramis software that automate some of that. You can do it automatically, or you can do it in a very controlled way. I think that's the best short answer I can give you. We'll be glad to look at your specific example, but I think that's a good short answer for you.
Okay, next question. How would you spray speckle on aluminum foam?
Aluminum foam. Foam, because of the, let's say, the little caves, or the non-flat surface. I've done different types of foam. If it has very high porosity, like an aluminum foam, the best approach there, honestly, sometimes is use a single camera looking straight at the specimen for a compression test. We just added some speckle within the porosity, and we actually got decent results. Other folks have done very low strength fill material. There's some potential issues with that, with its elasticity. For a foam, like a polyurethane foam with lower porosity, we've patterned it just in the usual way. I've got some foam specimens on the shelf here, just by coincidence. So it depends on the porosity. Sometimes normal patterning works just fine. Sometimes, because it's going to look so different from the left to the right camera in the stereo pair, for a really high porosity foams that have caves in them, the best approach is single camera looking straight and doing some supplement to the pattern. We're not going to be able to use the porosity itself as a pattern. We are going to need to apply a pattern.
Okay. Next question. What kind of lighting is recommended for DIC, knowing that high speed requires more illumination?
Right. Yeah, that's another great question. And both Photron and Trilion are always looking for what are the latest, greatest lights. So these days, LEDs have come a remarkably long way. We happen to have found one brand called GS Vitek, which is a German brand. They've got very small handheld light modules that are putting out 12,000 lumens and have swappable front lenses. You can put a 15-degree beam angle, or up to I think there's 4 beam angles available, up to very wide angle beam for concentrating all the light on a smaller area or looking at a larger area. So that's definitely the trend. Even for high speed now, there are bright enough LEDs available of all different kinds. Another interesting trend in DIC is to change from white light to monochromatic light. There are some benefits. So we, for lower frame rates, we can use blue LEDs. You do get less total light from blue. I was just looking at the specs, so I can read it out from my brain. The same light that does 12,000 lumens in white does 3,800 in blue. So again, depending on frame rate and aperture requirements, we're definitely going to go LED. We may go blue LED. And we've got some lights, because it's our job to supply the complete solution and not, good luck finding some lights. So we've got a number of different kinds of lights we've used over the years. We used to have 3 different model tungsten lights, the Lowell Pro and ARRI 650 Plus, but these days LEDs have come along far enough that we're almost always using LEDs, even for high speed. There is enough light from LEDs for even a couple of 100,000 frames a second. Beyond that, there are lasers. I know some of the Photron reps, like Tech Imaging, have some really interesting lasers made by Cavatar. I haven't used them personally, but I may need to use them before too long.
Well, let me just add this as well. That this is one of the reasons why Photron focuses so much on light sensitivity of the cameras. There's with the Nova camera being an ISO 64000, it's replacing the SA. One of the cameras that it's replacing is the SA5, and it's between 5 to 10 times more sensitive than that camera it's replacing. And the benefit of that, again, is you have to use less light than before, and you can stop those apertures down for a smaller aperture to increase your depth of field as well. So yeah, that's a big benefit about that as well.
Okay, a couple more questions. If you are measuring thermal strains, for instance, can you image in the infrared?
Yeah, that's a good question, and there's a couple of interesting answers to that interesting question. Yes, there are cameras that are sensitive in the IR, so that can be done. Similarly, at the opposite end of the spectrum, sometimes there's benefits to using UV cameras, especially at high temperature, to help suppress the radiant glow. Let me get rid of this, sorry. Normally, though, we're taking a different approach. We're using the white light or the blue light to like I'm doing work right now on these Glebel high temperature load frames up at 1300 C. So the approach we hear about and do more frequently is we're going to do the white light DIC. We're going to combine that with an IR camera to get the temperature. And then we can get very fancy. We can co-calibrate the IR camera to the Aramis stereo pair. So we can map the temperature from each pixel of the IR camera onto each data point in the DIC software. And then we can even do a correction. We can subtract out the thermal component of strain and leave only the mechanical component of strain. So that's kind of my complete answer if I hear the keyword IR and DIC, that's what I would say. I'm not sure. I'd be interested to hear more about this, why you might want to think you want to do direct DIC imaging in the IR. I mean, it can be done.
Okay. Next question is about vibration measurement. Is it possible to measure vibrations like accelerometers using this high-speed DIC system? And what is the maximum frequency that's measurable with such a system?
Right, that's a very good question. And while I'm starting to talk about it, I'll try to find, I don't know if I'm going the right direction. I think I'm going the wrong direction. I showed some very high G measurements in the post-processing of helmet data. Here it is. This was done at ARL SLAD, but it's showing the general idea. If we're talking about vibrations and DIC, the limiting factor is our displacement sensitivity, right? That's how we would differentiate from something like a scanning laser vibrometer. It's intrinsically sensitive to frequency, to velocity, and velocity is high as frequency goes up. Scanning laser vibrometer is great for very high frequencies, and it also has that interferometric level of sensitivity, so it can do very high frequencies with low amplitudes. Normally with DIC, we're working in the time domain, and in the time domain, we simply need enough microns of displacement. That's going down as frequency goes up. So the limit, I can't give you a firm number for, a cutoff frequency, but it's, are we able to excite enough displacement? And that does get tougher at higher frequencies. This is something I was just talking to some colleagues about, our new frequency domain tool that I just gave a hint at in today's presentation. We're then working directly in the frequency domain. Our effective displacement sensitivity goes up, so we can pull mode shades out at higher frequencies than we would be able to just the brute force time domain measurements. And we want to make some demonstration measurements of that very, very soon, like in the next couple of weeks or so, and have some demonstration data on how the frequency domain tools that we just recently developed enhance the ability to effectively work at higher frequencies and lower amplitudes. We have another tool in our toolbox to do that. We call it phase stepping. We can use higher resolution slow cameras only for single frequency excitation. Again, I don't have time to get into the details now. It's another way to have higher displacement sensitivity for DIC than we get in the brute force method of using high-speed cameras in the time domain.
Okay, next question. Can you record other channels during tests? For example, load signal from an MTS machine?
Right, that's a great question. And the answer is yes for all models of Photron camera and all of the slower rate, high resolution GOM sensors. They all have available as an option a data logger in one form or another. I briefly hinted at that on those femoral head, the hammer hits. We were using the Photron data logger, which is basically a National Instruments board plugging into the USB of the laptop. And the PFV software handles that in a very nice way. I'm sorry, I didn't actually show the example. We're using the camera clock to drive the data logger, and you have oversampling capability. You can tell it to log one signal per camera frame, or you can oversample by, let's say a factor of 20, and you can see the analog value between the high-speed camera frames if that would be useful. So, I mean, again, the short answer is absolutely yes, and it's built in and easy to do, easy to go set the scaling and convert from volts to force or whatever is appropriate.
Great. Thanks, Tim. And the last question we have is, could you send us the links to those courses you mentioned? That person seems to find these courses interesting. And I think the broad answer is that, yes, of course, but we also offer on-site or in-house here at Trilion training courses. But Tim, maybe you want to answer that question a little more?
Yeah, well, I certainly agree with everything you said, Jonathan. I mean, it's the same as the slide that Shane had prepared. All of this fancy features, both on the Photron cameras and maybe even more in the Aramis software, they're useless if you don't know how to use them. So training is really the most important part of our job and support, in our opinion. So. Absolutely, yes. I'll give you the links to the courses. It's the slides only. I'm probably going to add voiceover, which would make them more valuable. We do an initial 3-day training on site for every new customer, and then we've got quarterly training at Trilion, as we call it. We also have a dedicated support person. Usually it's our Sophia. So anybody running a test anytime, anywhere can call and say, help. And I mean, I personally have no limits on that. If it's 10 o'clock and someone's running a test somewhere and has a problem, this actually happened coincidentally with some Photron cameras. But don't worry, Shane, the problem wasn't really with the camera. It was just in the laptop setup. And I was able to just stop what I was doing and on the fly say, look, if we're not finding one camera in the stereo pair, the quick, easy, known solution, do a hard reset on the camera. Then it has a known IP address, hook it to a known Ethernet port, get back talking, and then, set it up the way you need it. So yeah, training and support go hand in hand. The more training we give, the less support we would have to give. So we're always looking to make more, I call it portable support solutions, self-contained videos that, just here's a link. This will tell you everything you need to know to answer the issue you're having right now.
Thank you, Tim. Thank you, Shane. This is the end of our Q&A and the end of this webinar. Thank you to all the attendees, and especially the ones who stayed until the end. If you have any more questions about anything that you've seen today or anything else related DAC or high-speed cameras, feel free to send us emails. Reach out to info@trillion.com. Thank you very much to everyone. Bye-bye.
Thank you.
Yeah, thanks, everyone.